Hello, this is Unit 10. We're talking about finding limits graphically today in this first lesson. And to begin with, we want to think about exactly what does it mean to find a limit. So there's one-sided limits and there's general limits. In a one-sided limit, we're going to write a limit from the left-hand side and a limit from the right-hand side using calculus notation. So I have a target value, that's my x value. I'm going to call that target value c in this case. And if I want to look at a limit from the left-hand side, I'm going to use a superscript up here and read this. The limit as x approaches c from the left for my function f of x. This is a left-hand limit from the left-hand side. So if I have a graph, and I'm looking at this graph, let's just say y equals x, and I want to look at the limit as x approaches 2 from the left. I'm writing the graph from the left up to the target value of 2. And similarly, the limit notation from the right would look like the limit as x approaches c from the right, so I've got a little superscript of a plus sign of f of x. And in this example, if I'm looking at the limit from the right, I would be heading toward 2 from the right, which would still be 2 in this case. When I talk about a general limit, I'm looking at the limit at a specific point. So when we write the limit as x approaches a for f of x is equal to a number, capital L, we get arbitrarily close to that number, that real number L. It doesn't have to be equal, but it has to be close to that number. A limit at a point is a function will have a general limit if the function is approaching the same y value from the left and from the right. So the left limit and the right limit have to agree in order for a general limit to agree. So we have to consider the limits at a hole, at a jump, and at vertical asymptotes. In those cases, we may have a situation where the limit does not exist. And we'll look at that in an example coming up. Then the limit definition of continuity is an important topic in calculus. And we say a function is continuous at a point. Then the limit is equal to the function value at that point, x equals a. And there's 3 conditions that are necessary. The first condition is that the function value is defined at that point, a. The second condition is that the limit has to exist. And then the third and most important condition is that the limit at your target number has to be the same as the function value at that target number. A function is continuous at a point if the limit as x approaches c, or in this case as x approaches a, from the left, and the limit as x approaches a from the right, they're approaching the same y value, and the y value is defined at this y value, at this x value. That should be an x. So again, we'll look at the particulars throughout the lesson. And in this case, let's look at something you're familiar with from Algebra 2 and earlier in pre-calc. The equation of the function is shown here below, and this is the graph of that function. And you may be able to go through and analyze the function completely. In fact, if you want, you can stop the video and write down a few of the key items that you remember from the beginning of the course. Maybe the domain and range, vertical asymptote, horizontal asymptote, and in behavior, if you can remember those things. Okay, so if you remembered some of that stuff, let's prove how we know the particulars about this function. If you factor the function, your numerator factors this way, and your denominator is the difference of two squares. So we have a common factor between the top and the bottom that we can remove since it forms a 1. So we're going to take out that form of 1. That also tells us that we know we have problems at -3 and +3. So before we removed the factor, there's a problem at x equals 3, and there's also a problem at x equals -3 because it'll cause division by 0 in the original function. Now simplified, we have an equivalent expression that represents the same graph. So we have a hole in the graph where we removed this factor. So at x equals 3, I want to find the value at 3 by substituting 3 into this expression, the simplified form. So 3 times 3 plus 1 gives us 10 in the numerator, and 3 plus 3 in the denominator is 6. So we have a hole in the graph at 3 and 10/6, and we could reduce 10/6 if we divide by 2 to be 5/3. So there's a hole in the graph here, and looking back at the graph, you can see this is where my hole occurs at 3 and 5/3. Okay. The domain of the graph is going to go from -infinity to -3, and then we're going to skip over -3 since there's a vertical asymptote here, x equals -3, and we're going to go from -3 up to +3, and then we're skipping over the hole, and we're going to go from 3 to infinity. So this is our domain. And then the range, if we read from the bottom to the top, we go from -infinity up to the hole, which is valued at 5/3. And then I believe we have a horizontal asymptote at y equals 3. Here the powers are the same, so 3 divided by 1 is my horizontal asymptote. So we go from 5/3 up to 3. And then on the other side, 3 to infinity. And you can tell by looking at the graph, we go from 3 up to infinity. So we had to skip 5/3. We had to skip the horizontal asymptote. And it was continuous everywhere except those two places. So we have the vertical asymptote at -3 and the horizontal asymptote at +3. So this is what we did back in Unit 1 when we analyzed functions completely, rational functions. So now here we're at the end of pre-calc, and we want to translate from pre-calc language over to calculus language. And at the beginning of the year, we said as x approaches -infinity, the graph of our function is approaching 3. And we can see that by looking at the picture again. As x approaches -infinity, so the further out we go here, when x goes out here, y goes to 3, because this is coming down, it's not going to cross the horizontal asymptote there. But in calculus, we want to write limit notation. So the limit as x approaches -infinity on our function f of x is approaching 3. And likewise, as we approach +infinity, if you take a look at the graph, the y values are approaching 3. So as x approaches +infinity, the function values are approaching +3. This is the limit notation for a horizontal asymptote. So we can use limit notation or pre-calc notation. We're going to want to favor this more. Then as we look at the x values, when x goes to -3 from the left, so let's take a look at that. As x goes to -3 from the left, that's this. As x goes to -3 from the left, the y values are unbounded upward. And as x goes to -3 from the right, the y values are unbounded in a decreasing fashion or downward. So this one's going up without bound, and from the right we're going down without bound. So these are the formal definitions for a vertical asymptote. As I head to my target number from the left, my function values are unbounded up, they're increasing, and as we head to x, our target value from the right, the function values are unbounded downward, or they're decreasing. And this is my formal justification for a vertical asymptote. And then finally, when x goes to 3 from the left, the graph of the function is heading to 5/3, even though it's not defined there. And as x goes to 3 from the right, the graph of f is heading to 5/3. So this is the idea that I have a hole in the graph, because the limit as we approach 3 from the left and the limit as we approach 3 from the right, they're both heading to the same y value, 5/3. Even though the function value is not defined at 3, it's getting arbitrarily close to 5/3. So since these are the same, that lets us know the limit from the left and the limit from the right are approaching the same y value, but there's a hole at that location because they're the same. You can kind of know that that's the value of the hole. So in this case, this is asking you to put into your own words how you feel about the explanation for what the value of a limit represents in terms of the graph. So turn the video off and write your own explanation and come back to check with mine. So I said something like this: a limit, excuse me, a limit is the y value that the graph is approaching from both the left side and the right side of some target value that we're calling C. The limit can occur at a hole, which is also known as a removable discontinuity. So if you said something along those lines, you have a pretty good understanding of a limit. Now, in this case, we're going to need a calculator, and I'm going to ask you to put this function into your calculator. And then we're going to look at the table value as we arbitrarily get close to -3 to explore that situation. So you can see I have my graph here. And if we switch over to evaluate, I want to evaluate at -3.1. So we want to evaluate the function at -3.1. That's 83. And then evaluate at -3 and 100th. And then evaluate at -3 and 1,000th. And then evaluate at -3. So you see it's undefined. And then going the other way from the right, starting over here at -2.9. Well, not 29, 2.9, 2 and 9/10. That's -77. And then at -2 and 99/100ths. And then at -2.999. So you can see the behavior of the function in that case. So we have 83 here, 803, 8003, and then we had the case of does not exist because it said undefined, and then coming the other way, -77, -797, and then -7,997. So as we approach -3 from the left and from the right. You see the behavior? It's growing unbounded, very large, increasing upward, unbounded in toward infinity. And from the right, we're getting unbounded, but in a decreasing fashion to negative infinity. So this is the way that we can explain a vertical asymptote, since the behavior is in opposite directions from the left and from the right at that target value of -3. So as we could explain this way, as x approaches -3, from the left, the y values are increasing. So y is increasing. And then as x approaches -3, from the right, y decreases. Therefore, x equals -3 is a vertical asymptote of the function. It's a vertical asymptote of our function f of x. Now the next example is for you to do, and then on your calculator, and then come back and check your work. So this is what my table looks like, and we're reading the calculus notation for limit as the limit as x approaches -infinity. So that's this way on that function is getting really close, arbitrarily close to 3, and as x approaches positive infinity, so that the larger values of x, we're also approaching +3. And we could explain that verbally by saying as x approaches infinity, y gets extremely close to 3, and as x approaches -infinity, y gets extremely close to 3. Therefore, y equals 3 is a horizontal asymptote of our function f of x. So here we're going to look at some graphs in example 3. The limit as x approaches 2. This is the general limit. So in order for the general limit to exist, we have to consider as we approach 2 from the right and from the left, where is the y value heading? So as we approach 2 from the right and the left, the y value is approaching 4. As we approach 2 from the right, this one says from the left, I'm sorry. So as we approach 2 from the left, the y value heads to 4. And as we approach 2 from the right, the y value heads to 4. And these are the same. So when the left limit and the right limit are the same, the general limit will exist. But the function value is not 4. The function value is -2. This is the function value. So that's a point discontinuity, a removable discontinuity. In this example, when we approach 1, that's our target value, approaching 1 from the left. So from the left, we're writing the graph up here, and it's heading toward 3. It's not defined there, but it's heading close to 3. When you approach 1 from the right, that's this branch. We're heading toward 1. These are not the same. They're different. They're not the same. So the general limit does not exist. There is no general limit. When the left limit and the right limit are different, there's no general limit. But the function value is 1. This is the function value, 1, 1. And in the third graph, the limit as we approach 2 from the left is going upward, unbounded. And the limit as we approach 2 from the right is also going up. And this is the same behavior. The behavior is the same direction. So it's increasing without bound on both sides in the same direction. but infinity's not a number. So really the general limit does not exist. But if we say infinity, this is a better answer because it tells me the behavior of the function. It tells us that the function is unbounded in an upward direction. So yes, the limit doesn't exist because technically infinity is not a number, but the behavior is infinity because it's unbounded in the same direction. And there is no function value at 2 since we have a vertical asymptote there. In example 4, we want to use the graph, that's a piecewise function, to find each limit. And if the limit doesn't exist, we want to say why. So using that graph, I'm going to turn on the double window so we can look at it at the same time. So looking at the graph, as you approach 3, the limit value is 1. As you approach 1 from the left, the limit value is -3. As we approach -2 from the left and the right, so the general limit is heading to -2. The function value at -2 is this point up here, so that would be 3. At positive infinity, the graph is increasing without bounds, so it doesn't exist, but it's going upward. As you approach 1 from the right, that would be this branch, our function is heading toward -1. What's the function value at 1? There is no function value at 1. There's none. And then the limit as we approach 2 is heading to 0 because that's on the graph, 0. The limit as you approach 5, it would continue up and that slope is 1, so it's going to head to 3. The limit value as x goes to -infinity, so it's heading upward, would be positive infinity. The limit as you head to -5, looks like it's going to, let's see, what's the slope? Up 1, 1, 2, 3, up 1, 1, 2, 3. So it's going to go to -5, -1 when it gets to -5. And then as you approach 0, how could we find that? Let's see. So as you approach 0, we're going to have to find the slope. This slope of this line is -1/3. And if we use the point +1, -3, we can write the equation of the line. Y plus 3 equals -1/3 x minus 1. So when you approach 0, y plus 3 equals -1/3 times -1. So we got -3. Y equals -3 plus 1/3. So y is heading towards -8/3 because that's -9/3 plus 1/3. That one took a little more work to figure out. Okay. And then this is the existence theorem. So the existence theorem says if the limit as x approaches c on some function f of x is a real number, if and only if the right-hand limits and the left-hand limits are equal to that real number. So based on what you've seen so far, does the y value need to be defined in order for a limit to exist? And we could say no, as long as the function approaches the same y value from the left and the right, the limit will exist. So I said it's something like that. And then in our final example, we want to draw two different graphs where the y value is not defined. One graph shows how the limit exists, and one graph is going to show how the limit does not exist. And we need to explain our reasoning using those three conditions. So let's say we have the limit as x approaches c for our function, and this one is going to exist. So I'm going to put my c value right here with the hole and just draw some curvy little line right there. So how does the limit exist? First of all, the function is not defined because our x equals c, I don't want to say x, yeah, well, we'll say because at x equals c is a point discontinuity. But the limit as you approach c from the left is equal to the limit as you approach c from the right. Therefore, the limit at c on our function exists. Function value is not defined there, but this is the limit. Whatever that number is, this would be our real number. And then this one where the limit does not exist as x approaches c on f of x, and I'm going to use letters, does not exist. We'll put c over here, and let's say we have some value here, and then down here we have another branch. And to explain that, we could say, let's see, did they say we had to have f of c is not defined? So f of a, they want me to use a. I'm using c. I think my old textbook had a c there. So we need to have a. So first of all, f of a is not defined like they asked us to do. And at x equals a, in this case, we called that a jump discontinuity back in chapter 1. That's a jump discontinuity. And the limit as x approaches a from the left of the function is not the same as the limit as x approaches a from the right. Therefore, the limit as x approaches a for our function does not exist. And these should all be little a's, not c's, since they told us to use f of a. Okay, that's the end of lesson 1. See you for lesson 2.